All right, the fundamental theorem of calculus is such a big deal that there's two of them. It is twice as fundamental. So, on page 288, let's do a little reading. It says, earlier you saw that the definite integral of f on the interval from a to b was defined using the constant b as the upper limit of integration and x as the variable of integration. However, a slightly different situation, I'm not sure the word slightly needs to be in there, may arise in which the variable x is used as the upper limit of integration. Now, this causes notation troubles, okay? Remember when we were doing the chain rule, and we'd have a chain rule inside of a chain rule, so we'd have a u, then we'd have another u, but we went ahead and called it u, and just, so we got some issues with that. So, to avoid the confusion of using x in two different ways, t is temporarily used as the variable of integration. Now, the two different ways, I'll put it in here in green, I don't know if you can see it. X would be used as the variable of integration and as the upper limit of integration, and that's just weird, right? You don't want to use one letter to do two different things. So, we're calling t the variable of integration. So that means our function is now f of t, okay? So remember that the definite integral is not a function of its variable of integration, because a definite integral is a number, isn't it? It's a constant, okay? So, the definite integral is a number. This is what we were doing yesterday, isn't it? We were evaluating these. All right, we'd have something like the integral from -1 to 1 of x squared plus 3 in a parentheses dx. So, and we'd get a number. So the definite integral is a number. But if we write it this way, like they have on the right here, the definite integral is a function of x. Notation troubles again. Capital F of x, okay, so they're telling it it's a function of x, equals the integral from a to x. A is a constant, x is x of f of t dt. So we've just defined it this way. Okay, so now we're calling the definite integral a function of x, and we've defined it this way. What does this do for us? Well, it does this. Let's take a look here at example 6. They want us to evaluate the function, and then it's a definite integral as a function of x, isn't it? All right, capital F of x equals this definite integral. So this tells us it's a function of x. We need to start recognizing that that also tells us it's a function of x, okay? But f of x, so it's a function of x, equals the integral from 0 to x of the cosine of t dt. They want us to evaluate this function for 0, for pi over 6, pi over 4, pi over 3, and pi over 2. Now, we could work this out by replacing x with 0, work it out as a definite integral just like we did yesterday. Then we could replace x with pi over 6, work it out as a definite integral just like we did yesterday. And then pi over 4, pi over 3, pi over 2. We can do that. We can. Or we can do this. So it says you could evaluate 5 different definite integrals, one for each of the given upper limits. However, it is much simpler, much simpler to fix x as a constant temporarily to obtain, okay, so we play along here. We've got the integral from 0 to x of the cosine of t dt. That's just our function, isn't it? All right, so we've worked that out, but let's work it out. Now, yesterday we were just doing algebraic functions when we were doing definite integrals. This one's trigonometric, but the antiderivative of the cosine of t dt is the sine of t. So the sine of t is the antiderivative of cosine of t. So we're at this stage, right? Capital F of x evaluated from a to b. That's what that is. It's a t, capital F of t, evaluated from a to b. Okay? And then what we learned yesterday, the way to evaluate these definite integrals is it's capital F of B minus capital F of A. So there's capital F of B, there's capital F of A. Well, fortunately for us, the sign of 0 is 0, so we just get the sign of x. So look what we've got. Look what we're saying. We've done the work, so we can prove it. We're not just making it up. We're saying that the integral from 0 to x of cosine of t dt equals the sine of x. Now, won't it be fairly easy to evaluate for those different x's? See, now it's a lot easier problem, isn't it? Okay? So now using capital F of x, capital F of x equals that, so therefore it equals that as well. You can obtain the results shown in figure 4.35. So then they work them all out. So when x equals 0, the sine of 0 is 0. When x equals pi over 6, the sine of pi over 6 is 1/2, and then so forth. And notice that when you look at it graphically, that you're also getting areas. What's a definite integral? You ought to get areas, shouldn't you? Because that's what a definite integral is, a signed area. So it all is tying in together, I hope. Okay? All right. It says in example 6, note that the derivative of capital F is the original integrand with only the variable changed. Really? The derivative of what did they say? The derivative of capital F is the original integrand. If capital F equals the sine of x, the derivative of the sine of x, yeah, they're right. It's just with a different variable. Okay? So let's see how this works out. So if you have the derivative, and all this is using substitution. I had to make a note to myself there to remind, so you would see where this is coming from. So the derivative of capital F of x equals the sine of x. Remember? We said so right here. Capital F of x equals the sine of x. So that's the derivative of the sine of x. Well, the sine of x equals this. So substitution again. So replace the sine of x with that definite integral, the integral from 0 to x of the cosine of t dt. And since we know that the derivative of the sine of x is the cosine of x, that means this, and this are all equal to each other. With me? Okay. This result, the result being that the derivative of capital F of x is the original integrand, this result is generalized in the following theorem called the second fundamental theorem of calculus. I've read lots of authors here in recent years that claim this should be the fundamental theorem of calculus, that this should be. And, you know, I kind of agree with them because this ties together, well, you'll see. If little f, is continuous on an open interval I containing A is a constant, then for every x in the interval, so whatever that interval is, x is in it, then for every x in the interval, the derivative with respect to x, that's what that notation means, isn't it? Like when we write dy dx, we mean the derivative of y with respect to x. So d over dx means the derivative with respect to x of the integral from a to x. A is a constant, x is your upper limit of integration, of f of t dt, it always equals f of x. The derivative of the integral gives you the original integrand back. Now, those of you with color issues may struggle a little bit here, but I tried to, here's what's got to work out. It's got to work out this way. See where I've got the Well, first, the lower limit of integration has to be a constant. I don't care what it is. It could be 0. 0 is the most common just because. It can be 10. It can be negative 2/3. But the lower limit of integration has to be a constant. And then, where the yellow dots are, those variables have to be the same. So the derivative, if the derivative is with respect to x, then the upper limit of integration has to be x, and your function will be in terms of x. Yeah, it could be r. No, not for us. Okay? I can't speak for what comes later because I haven't had calculus since the early 80s. I only remember what I teach. So it's got to be the same there. The derivative with respect to x, the upper limit of integration x, the resulting function in terms of x. And then where I have the blue dots, those have to be the same. All right? F of t, dt. Could be f of r, dr. Could be f of q, dq. Dq. All right? But that's got to match up. So what we are saying is this, that the derivative of this function, this integral as a function of x, is the original integrand. The derivative of a function written as a definite integral is the original integrand. Doesn't that kind of make sense? Ignoring the x's and the t's for a minute, shouldn't the derivative of the integral be the function? Well, because integration is antiderivatives. We've been using the word integration to mean finding the limit of the sum and getting the area under the graph. And we've been using the word integration to mean antiderivative. So if we think of integration as being antiderivative, shouldn't the derivative of the antiderivative be the function? Right? It's just like if you multiply by 5 and then divide by 5, don't you get your original number back? Because multiplying by 5 and dividing by 5 are inverse operations. So if you take an integral, then you take its derivative, you ought to get the function back. Okay? The integrand is whatever you're taking the integral of. Okay? All right. Now let's see how this works in practice. So let's look at example 7 on page 290. It says, to use the second fundamental theorem of calculus to evaluate the derivative with respect to x of the integral from 0 to x of the square root of t squared plus 1 dt. So I've recopied here our formula. Formula is maybe not the right word. Our equation, our definition that goes with the second fundamental theorem of calculus. So let's see how it plays out. All right, so I've got the derivative with respect to x, like I'm supposed to have, of the integral from 0 to x. Integral has to be from a constant to x. Is 0 a constant? Yep. So it's working right, from a to x of f of t dt. Well, so that's f of t, and the square root of t squared plus 1 is f of t dt. According to the second fundamental theorem of calculus, our answer, the derivative of that integral, is f of x. So if that's f of t, isn't that f of x? Just x instead of t? Well, remember, the only reason that's a t is because they didn't want to use x in two different places in two different ways. So we're dealing with a function of x all along. We just tried to be as tried to be not as confusing as we could be if we really wanted to be. How's that? would be, it wouldn't change anything. Like if there was a 3 there, then if f of t is 3 squared of t squared plus 1, f of x would be 3 squared of x squared plus 1. Even if you factored it out, don't factor it out. Because then we'd have to use the product rule, and no, don't factor it out. Yeah. Do what? Yep. All you're doing is, now remember what this is. It's the derivative of a function defined as a definite integral. Okay? That's, a minute ago, three screens ago, we were calling that capital F of x, right? So the derivative of a function defined as a definite integral is simply the integrand. Make sure you get the right variable back into it. If it's the derivative with respect to x, it'll be f of x. If for some reason we made it the derivative with respect to q, then it would be f of q. Okay? All right. Says this is a straightforward application of the second fundamental theorem of calculus. The next example, which we'll get to in a minute, shows how this theorem can be combined with one of our favorite things, the chain rule, to find the derivative of a function. All right, before we get to that, let's not lose sight of what we're doing here. So the next thing I'm going to do is we're going to work a problem from your assignment that tries to show you the value of the second fundamental theorem of calculus. Because I'm afraid you might be sitting there thinking, I kind of sort of get this, but I'll just take the integral and then the derivative of that, and it'll all work out okay. Which, you're right, it would. It'd just take you a whole lot more work. Okay? So, let's do number 76. On page 293, number 76. We have two parts to this. Part A, integrate to find capital F as a function of x, and then part B, demonstrate the second fundamental theorem of calculus by differentiating the result in part A. So the first thing we have to do is pretend for a moment that the second fundamental theorem of calculus does not exist. Okay? Which some of you will find very easy to do. So we have the capital F of x equals the integral from 0 to x of t times t squared plus 1 dt. Let's simplify, or let's find that integral. Okay? Now, to find the integral of t times t squared plus 1 dt, I can't do it like it's written because there is no product rule for integration. So distribute the t. So capital F of x equals the integral from 0 to x of t cubed plus t dt. Now can I find the antiderivative? Sure, now I can. So capital F of x equals 1/4 t to the 4th plus 1/2 t squared, evaluated from 0 to x. So that's this stage, isn't it? That's the stage we're at. We found the antiderivative, and we're going to evaluate it from 0 to x. Remember how that works. It works this way, right? That becomes capital F of b minus capital F of a. So first we evaluate for the upper limit of integration. We put a minus sign. Then we evaluate for the lower limit of integration. So capital F equals 1/4, then substitute an x, because that's your upper limit of integration. Substitute x in for t. So 1/4 x to the 4th plus 1/2 x squared. So that's the antiderivative evaluated for the upper limit of integration. Minus, and now we evaluate the antiderivative for the lower limit of integration. So 1/4 0 to the 4th plus 1/2 0 squared. And all that turns into a 0. That's kind of nice. So capital F of x equals 1/4 x to the 4th plus 1/2 x squared. And remember that we don't have a plus c, because if we had of, we would have had if we had a plus c there, we'd have a plus c there, a plus c there, then that plus c minus that one would give us a 0 anyway. So that's why we don't bother writing them in when we do definite integrals. Joseph? Yes. Yep. Now, so we've done part A. Part B says, demonstrate the second fundamental theorem of calculus by differentiating the result in part A. So let's pretend I don't understand that yet. I understand this. Differentiate the result in part A. So take the derivative of what we just found. Okay? So if capital F of x equals 1/4 x to the 4th plus 1/2 x squared, the derivative of capital F of x, capital F prime of x, equals, well, what's the derivative of 1/4 x to the 4th plus x? Okay, so now I say, okay, I've done the derivative. Demonstrate the second fundamental theorem of calculus. The second fundamental theorem of calculus says that the derivative of that would equal f of x. And what would f of x equal? It would equal that, correct? So all I got to do is factor an x out, and I have demonstrated the second fundamental theorem of calculus. Yeah. Yeah. And look, the notation gets confusing. It does to me, because I meant to say little f of x, but I just said f of x. You're like, well, which f are you talking about, the capital or the little? And, so it can get really tedious, but that's the way it is. All right, you with me? Okay. So, look how much easier, and this is the point of a problem like this. Look how much easier doing that is than doing that. Okay? So, learn the second fundamental theorem of calculus, know it, love it. Number 86. Use the second fundamental theorem of calculus to find capital F prime of x. Now, let me caution you about something here. We're going to get so used to seeing this and applying the second fundamental theorem of calculus that sometimes we forget what the second fundamental theorem of calculus is for. It's for finding the derivative of a function that's defined as an integral. Okay? So here's what I've seen students do in the past. They'll take something like that, and they'll forget that the second fundamental theorem of calculus means to take the derivative of that, and they'll just say that that equals f of x. And it doesn't. Does it? The derivative of it equals f of x. So there's your warning. Okay? So make sure that we're finding the derivative, and we are. Says so, right there. All right. So if capital F of x equals the integral from 0 to x of secant cubed t dt, our second fundamental theorem of calculus, and you don't really have to write this step in, but is your example, write it in. The second fundamental theorem of calculus means to find the derivative. So the reason I want you to write it in as an example is I want you to get used to both notations. That means find the derivative of the integral from 0 to x of secant cubed t dt, and putting the dx in front also means find the derivative of the integral from 0 to x of secant cubed t dt. So notation's an issue, but make sure you recognize that saying capital F prime of x and saying d dx of that integral mean the same thing. Okay? Well, what's the answer? Yeah. That must be f of t, so that is f of x. So big F prime of x equals secant cubed of x. Right? Because we're taking the derivative of an antiderivative.
So for the notation, that big F, big prime of F,
Uh-huh. I know what you mean.
yeah, that's big prime.
Yeah. All right. You hanging in there with me? Okay. All right. All right. Extra example number 1. Write this down. Because our book does not give us enough of these problems to work. So I had to make up, I'm sure I found it from a book somewhere, but I had to get some more stuff. Okay? All right, we're going to use the second fundamental theorem of calculus to find dy dx when, all right, so instead of calling it capital F, look what I'm calling it this time. I'm just calling it y. So instead of calling it capital F of x, I called it y. Equals, we integral from 0 to 3x of the square root of 4 plus t squared dt. And this is not exactly what we've been doing. Do you see what's different? It's a 3x instead of an x. Okay? Now, remember the chain rule. That can be like your battle cry when you're studying. Instead of remember the Alamo, remember the chain rule. We had 2 different versions. Well, we had at least 2 different versions. One way we thought of the chain rule was like this. It's kind of my favorite. Dy dx equals dy du times du dx. What does this mean? This means the derivative with respect to u, but then we had to take the derivative of u. Okay? Remember doing that? We did that a million times, right? We would say something like, don't forget du dx. All right? Another way we wrote the chain rule was like this. F prime of u times du dx. Well, that's just a different way of writing dy du. F prime of u, doesn't that mean the derivative of f with respect to u? Since we called it f prime of u, not f prime of x. So the first thing to do is to take the derivative of your function with respect to u. Either way it's written. Isn't that what we're saying? And then times the derivative of u. Now, what's this u I keep talking about? What's that right there? We wanted it to be an x, but it's not an x. It's a u. Okay? All right, now, I copied it down again so we'd have it fresh in our minds. The second fundamental theorem of calculus says that the derivative with respect to x of the integral from a to x of f of t dt equals f of x. Now, let's apply all of this, the second fundamental theorem of calculus and the chain rule, to our problem. So, y equals the integral from 0 to 3x of the square root of 4 plus t squared dt. Let u equal 3x. Okay? If u equals 3x, that means we can rewrite our function as y equals the integral from 0 to u of the square root of 4 plus t squared dt. Now, I wrote the chain rule down again next to it because I'm going to apply that. So look what I need to do first. To find the derivative of the integral from 0 to u of the square root of 4 plus t squared dt, the first thing I do is take the derivative with respect to u. Well, if that was an x, we'd get square root of 4 plus x squared, correct, as our derivative? Well, it's a u, so we get, oh, I forgot I rewrote it like this. Let's skip that for a moment. So, the derivative of that with respect to u is the square root of 4 plus u squared. That's the second fundamental theorem of calculus, isn't it? All right? The derivative of what I have circled in red equals the other thing I have circled in red. That's a direct application of the second fundamental theorem of calculus. Now, the chain rule says times the derivative of u. Well, if u is 3x, and this is what I had covered up here, if u is 3x, isn't the derivative of u 3? It wasn't there. I had it covered up. So the derivative of u is 3. So, times 3. Yeah, there's a whole lot of theory going on here, and it turns out to be kind of simple, doesn't it? Now, we're supposed to find dy dx. Do we have everything in terms of x? We got u. So what do we do? Yeah, replace the u with 3x, and then since we square that, it becomes a 9x squared.
I understand that 3 to the
Uh-huh.
then from the integral.
Yeah, I will. I'll go over it again. All right. Let's go back up to here, and let's look at the notation I wrote out. Okay? We skipped it for a minute. I wanted to skip it, but I also want to come back to it. All right. That's our function. We've now rewritten the 3x as a u, okay? And we're supposed to take the derivative of y with respect to x. So on the left side, take the derivative of y with respect to x. Then on the right side, look what this turns into. dy du means d du of that function. All right? That is the second fundamental theorem of calculus, just with a u instead of an x. Okay? You follow me? That, see how that is the same thing as that, just with a u instead of an x? Okay? And then chain rule times the derivative of u. With me? Okay, hang on. So now all I got to do is apply the second fundamental theorem of calculus right here. The second fundamental theorem of calculus is I get f of x. Well, it's not x. We said it was u instead of x. So it's f of u. And then still times the derivative of u, which is 3. And then we go ahead and switch it back to x. Does that help? All right, now, I really want you to understand what we've done here. I really do. And we can do some more of these. But when you cut to the chase, look what happens. You get that. You just put 3x in for t, don't you? Times the derivative of u. You see what happened? So you really do, I mean, it can be, and we're going to work these as 2 or 3 step problems. We're not going to write all this out every time. I want you to understand how it works. But to make it work, you're really just going right back up here at the top. You're replacing t with 3x. And then, but you've got to remember, since this is a chain rule problem, times the derivative of u. Didn't I say that a million times back in the fall when we were learning the chain rule? Times the derivative of u, because it's a chain rule problem. It's a chain rule problem, so times the derivative of u. Any questions? Alex? No. Well, don't make it a t. You work it the same way. You just be putting in an x squared for t instead of a 3x. Okay? So, take a minute to read example 8. They use a little bit different notation, but see if you can follow their example 8. And I think you'll find that they did the same thing we just got through doing. What'd they do with what? It's the constant. It just kind of goes away, doesn't it? Mm-hmm. The theorem says so. So now, let's cut through it all. No. F prime of x equals, take your integrand, replace t with x cubed, chain rule, times the derivative of u. All right. Questions on example 8? That is the derivative of that. Uh-huh. Do that one. Find the derivative. Find capital F prime of x. Get the first step right. Replace t with u, and then times the derivative of u. Replace t with x squared times the derivative of x squared. And then that's what you ought to get when you're through simplifying.
Yeah.
And remember, the second fundamental theorem of calculus is used to find the derivative of an integral. But not just any old integral. The derivative of an integral that is a function of x. Okay? Or a function of x that's an integral. Maybe a better way of saying it. All right? Everybody got it? Some of you have happy faces and some of you have, oh, what happened face. Do that one. Find capital F prime of x for this one. Any questions? Yeah, copying it down wrong hurts your chances. Yeah, so then you got to make a mistake to cancel out you're copying it down wrong. Or you can go back and recopy it correctly. All right, we good? Cubing the 3x. All right, number 88. So back to the book. We're supposed to find capital F prime of x. Now, even though we now know the second fundamental theorem of calculus and we're really, really good at using it, it's not always the best method to use. In fact, it doesn't apply here. Why not? Because we don't have a constant as our lower limit of integration. Add x to both of them. No, we could use the fact that we have an odd function. We could do that. But the reason I chose this one to work out, though, is so that you could see this. That's capital F of x, isn't it? Take the integral, evaluate it from negative x to x. So first, we substitute x into our antiderivative. We put a minus sign. Then we substitute negative x into our antiderivative. Now, this stage is here. Now, it's a different capital F, isn't it? It's not the, maybe I should call it capital G. Evaluated from A to B, and then it's capital G of B minus capital G of A. This is using yesterday, using the fundamental theorem of calculus. So, our function is 0. What's the derivative of 0? Uh-huh. Because when I raise negative x to the fourth, that's a positive x to the fourth. So 1/4 x to the fourth minus 1/4 x to the fourth is 0. It did. Now, let me go back up to here. That shouldn't be surprising, because y'all were wanting to do this. Y'all were wanting to mess with the integral. T cubed is an odd function. So the integral from negative a to a of an odd function is going to be 0, because there's just as much region below the x-axis as there is above the x-axis. The signed areas are going to add together and give you 0. So some of you kind of saw that coming. You just didn't know how to say it. Or maybe you did and I didn't know how to hear you. Okay? All right, you with me? Now, we can use the second fundamental theorem of calculus to work that problem. So, when you watch this video, notice I didn't say if. When you watch this video, you can hit pause right now and take a look at that work. Yeah, then you gotta know to unpause on your own, because once you've paused it, you won't hear me say unpause. So I guess I could say play. Here you go, page 291, 75 through 92. And if you didn't do those extra two that we did, extra number 2 and extra number 3, do them now.